Okay, welcome all. We are happy to have Professor MALABIKA PRAMANIK as the Jubilee Chair Professor for this year, 2024. So she has been in India for a while now. Here she'll be giving 2 talks, and there is also a public lecture on 19th at the planetarium. So today is the first lecture. She'll be talking about the geometry of distances, a tale of points, patterns, and problems. Okay, so Malavika.
First off, I'm very grateful to the Indian Academy of Sciences for enabling my visit here. I would not be standing in front of you today were it not for a few individuals that I would like to acknowledge. Professor Gadadhar Mishra and Professor Kalyan Sinha, who envisioned this opportunity and made this possible, and my teacher and S. Thangavelu and my old friend Professor Narayanan for making all the local arrangements over here. Thank you all. Okay. So I wanted to talk to you today about 2 extremely elementary notions, points and distances between them. Now these concepts occurred at the dawn of civilization in many different cultures, and back then the idea behind these questions was things like, well, what is the diameter of planet Earth, or how far am I from the sun, questions of that nature. But what I want to prove to you, try to convince you today, is that the notion of distance between points remains an incredibly rich source of problems, even in modern mathematics, and the driving force in many new areas. So here is a plan of my talk. I will start by describing what distance problems are in the modern parlance and why we should study them. This will be followed by a sample of problems, some in the discrete setting and some in the continuum. And later, if time permits, we will talk about some results and proof ideas, but I'm hoping to relegate most of this to tomorrow's talk. Okay. So let's get started. What are distance problems and why should we study them? All right, so suppose that x and y are 2 points in d-dimensional Euclidean space denoted by RT. x1 through xd are the entries of x. Then the ancient and venerable Pythagorean theorem tells you that the distance between x and y, denoted by x minus absolute value of x minus y, has the following definition. Its square is the sum of squares of the differences of the individual entries xj minus yj. Okay. The concept of a distance between points gives rise to the notion of a distance set. What is a distance set? So suppose that capital P is a subset of Rd. The distance set of P, which I am going to denote by delta P, is simply the collection of all pairwise distances of the points of P. Namely, it's the collection of numbers of the form absolute value of x minus y, where x and y both belong to capital P. So P may reside in any ambient dimension. Delta P, however, is always a subset of the non-negative real line, and 0 is always going to be an element of delta P. Some examples are in order. Suppose that capital P consists of the first n non-negative integers, then delta P is the distances between these integers, and if you give this some thought, is just the same as P itself. Okay. Suppose now P is a collection of 3 points, the vertices of an equilateral triangle in R2 of side length 1. Delta P then consists of 2 numbers 0 and 1. What happens if you now take capital N many points in general position in RD? What does that mean? That means the distances between these n points bear no special relation to each other. In this case, one can see that if you take throw away the trivial element 0, the first point in capital P generates n minus 1 distances, the second one generates n minus 2 new ones, and on you go. So when you sum them up, the number of non-trivial entries in delta P is n times n minus 1 over 2. Okay. And I'll close this discussion of examples by looking at cubes and intervals. Let's say QD is the unit cube, d-dimensional unit cube in RD. Then the distance set of Q sub d is an interval 0 to square root of d. The square root of d is of course realized by the diagonal. Okay, so now that I have told you what a distance set is, what are the questions? So everything in this talk is going to be driven by this meta principle. Large sets should have large distance sets. So this is kind of a mantra that I'm going to keep coming back over and over again. Sets are large because they have many points. And if a set has many points, somehow they have to generate lots and lots of distances. And the question is, how do we quantify lots and lots? Okay. So for capital P of a given size, how large or how small can delta P be? What are the extremal configurations? In other words, what is the class? Can one characterize the sets of points where delta P has the largest size or the smallest size? And of course, these are very loosely framed questions. How does one measure size? What do I mean by large and what do I mean by small? So these are going to be the questions that we want to deal with today. Before we head out into the problems themselves, the question is, should we care? Now, I know in a way that I'm preaching to the choir here. You are all mathematicians, so you don't need convincing. Any problem that is puzzling is of interest, but perhaps there are people out there listening to this talk wondering, really, is there any point to this? So for those of you out there, this is my response. So distance sets, by their very simplicity, have of course caught the attention of many scientists, but even within mathematics, their impact is really far-reaching. They have brought about new areas of combinatorics and analysis. They have reached out into number theory and geometry, and they currently have, most recently, they have found applications in information theory and computer science. Now, these distance problems, by their very nature, are gateways into many beautiful areas of math, and I'm hoping that in the limited confines of this talk, you are going to get a glimpse of some of these areas. Okay, so I'm going to head into the problems now. Any questions so far? Yes.
So in this discussion, will the geometry of space, whether it's Euclidean or non-Euclidean, will that enter in any manner?
Well, in today's talk, in some manner, so sets that are Euclidean in nature will play a more prominent role, but you are very welcome to ask me at the end of today's talk and end of tomorrow's talk, what are the sort of multitude of other spaces where such questions could be reframed. And in fact, some of it has already been done, and some of it is still uncharted but very exciting territory. Okay, so today we are going to talk about discrete and continuum in the Euclidean setting mostly, but of course these questions make sense in many other spaces, in hyperbolic spaces, on the Heisenberg group, in Riemann symmetric spaces, and the whole lot. Okay. Any other questions? Is there any question from the chat? I'm hoping that somebody will keep an eye and let me know if there is any. So Apurva is a tech guru, so I'll just leave that to him and continue. Just let me know when something pops up, okay? All right. So I promised you a small sample of problems, both in the discrete and in the continuum setting. So here's some problems in the discrete. So everybody, all of us know Paul Erdős, and he is you will see the two problems in the discrete setting that I want to mention today, both bear his name. Okay. The first one is called the Erdős distinct distance problem. So what does that ask? So we are in dimension D, at least 2. We are going to denote by G sub D of n the minimal number of distinct distances that an n-point set in Rd can have. So, in other words, we are looking at the collection of the cardinality of delta p, the collection of the distance set of p, and then taking the minimum such cardinality as capital P ranges over all subsets of Rd of size n. The question is, how does G sub D of n grow with n? And Erdős conjectured the growth rate. So for D larger than or equal to 2, the claim is that there exist absolute constants depending only on the dimension, such that G2 of n behaves like capital N over square root of log n up to these constant multiples. And for D larger than or equal to 3, the growth rate is like capital N to the power of 2 over D. Okay. Usually at this stage, I stop and ask and wait for a question, and I'm hoping that some brave soul in the audience will ask me that question. Yes. Yeah, wow. Where did Erdős get these numbers from? Where did they come from, right? Usually there is some deep mathematics hiding behind conjectures, and thank you for that. And this is his motivation. Okay, so the motivation for the conjecture was the square root of n by square root of n integer lattice. So in dimension D equal to 2, this is an n-point set. Right? And suppose we are trying to look at the distance set of this integer lattice. So let me draw a picture here. So these are integer points, and this is a natural number m, this is a natural number n. So if this is D, then D square is m square plus n square, which means that all the distances that can occur in this particular set has to be the square root of, it has to be a sum of 2 squares. Okay, so sum of 2 squares. And there are classical, so this kind of takes you into a number theory problem. And there are classical number theory results due to Landau and Ramanujan that actually gives the asymptotics of such points. it tells you how many distinct numbers there can be which are of this form less than or equal to n. And that is exactly n over square root of log n, and this gives us an upper bound on G2 of n, and Erdős's conjecture was that this is an extremal configuration and this is the lower bound as well. Does that make sense? Okay. All right. So this is a long and still inexhaustive list of the progress on the Erdős distinct distance problem. The conjecture has almost been solved in dimension 2. It's a celebrated result of Larry Guth and Ned Scatz. In 2015, they showed that G2 of n is bounded from below by n over log n. Remember that the conjecture requires this there to be a square root, but up to that square root factor, this is sharp. The problem is still open in dimensions 3 and higher. The current best known result is off of the sharp exponent by a term of the order of a constant over d square, and this is due to Van Wu and my UBC colleague Joseph Solimushi. Okay. Yes?
So for 3 and higher, there are asymptotics from number 3 is on the 3 scale.
Yes. So this one, so this is the Landau-Ramanujan, this was only for R2, but now there are exactly the right kind of asymptotics which give you the upper bound for this. So the lower bound is the one that's open. Thank you. Okay, all right. So I'm not going to be able to, even if I tried, to give you an idea of the Guth-Katz result. It's a beautiful piece of mathematics, and I strongly urge you, those of you who are interested in problems of this flavor, to either look at their paper in the annals or to look at the many blogs about their work that have been written all over the world. The proof is based on a technique known as incidence geometry. So what I want to do rather today is to give you just a flavor of what an incidence geometry argument looks like. It's a really baby version of an incidence geometry argument, but maybe that's all that we can do today. Okay. So what I want to show, so this argument is due to Erdős, the father of this conjecture, and he showed way back when that G2 of n is actually bounded from below by square root of n by an incidence geometry argument. Of course, you realize that this is nowhere close to being sharp, but it's the argument that I'm trying to get across to you. Okay. So in this picture, these black dots that you see, those are the points in my n-point set, capital P. Okay. I am picking one such point, little p, and what I'm going to do is I will start drawing these concentric blue circles centered at P. Each blue circle has to pass through at least one point of capital P. Perhaps it will pass through many. Okay. And I repeat the same exercise with another point P prime, giving rise to a family of red circles centered at P prime and passing through at least one point in capital P. Okay. So because it's a finite point set, at the end of this exercise, we are going to get a few blue circles and a few red circles. Let's say there are S many blue circles and T many red circles. Okay. So I'm just going to, this is the sketch of the argument. So we start with P, fix 2 points P prime, draw a family of S blue circles centered at P that cover capital P, and we do the same with P prime, and we obtain a family of T red circles. Let's wait for a moment to check that G2 of n is bigger than or equal to S. Why? What is S? S is the number of blue circles. Every circle corresponds to a distance in the set. But not all distances may be covered in such a way. Therefore, G2 of S, which is the set of all distances, is bigger than or equal to S. Okay? Similarly for T. Okay. Now, as these two families of circles intersect, capital P must be contained inside of the intersection, right? Because that's how they were chosen. But it's a property, it's a geometric property of circles that two circles can intersect in at most 2 points, which means that the total number of points of intersection is at most 2 times ST, and this 2 times ST must therefore exceed the total number of points in the set except possibly P and P prime, which means that 2ST is larger than or equal to n minus 2. But if the product of ST is larger than n minus 2, then either S or T must be at least square root of n, and therefore G2 of n is at least square root of n. So this is kind of a, as I said, a tiny flavor of an incidence geometry argument. You take a problem, you cast it in terms of some geometric objects, see how those geometric objects intersect, and the properties of the intersection give you a bound of the object that you are trying to estimate. Okay. Okay. So one might say that the Erdős distinct distance problem has somewhat of a happy ending, at least in dimension 2, because it's almost solved. But here is yet another distance problem which is very far away from a resolution as of yet. It's called the Erdős unit distance problem. So once again, we start with, I'm just going to state this in dimension 2. There is a corresponding version in all dimensions. So take a point take an n-point set capital P in the plane and look at the maximum number of pairs P comma Q inside of capital P which are separated by distance 1. We are looking at the maximum cardinality of such point pairs, and we are going to denote that quantity by U of n. So U of n is the largest number of pairs in an n-point set, which is a fixed distance apart without loss of generality, 1. Okay. Same question, how does U of n grow with n? By now, it would not surprise you that once again, the motivation for conjectures come from number theory, Erdős conjecture that U of n has to grow like this, and he went back to that square root n by square root of n lattice example. There were results available due to Fermat and Lagrange, and that's what generated this conjecture. Erdős himself worked on this problem and obtained an upper bound of n to the power of 3 halves, which were later improved by several authors. But the best known result on this problem, which is by now exactly 40 years old, is due to Spencer, Zeberedi, and Trotter, and the exponent stands fixed at 4/3. Okay. All right, so I know that I cannot give you a sort of a good answer to this problem, but I do want to tell you how sometimes the journey is probably worth more than the destination, and this is one such example. Because in the process of trying to understand this distance problem, some of which are still like tantalizingly out of reach, people have generated an incredible amount of beautiful mathematics. And here is one such example. So Erdős, while working on these distance problems, he introduced this concept which has now become kind of a workhorse, a cornerstone in combinatorial geometry. And again, I just want to give you a sense of what such an argument looks like. Okay? So what he does, he takes a distance problem question and casts it in the language of graphs. What is a graph? A graph is a collection of vertices and edges. Certain vertices are joined by an edge, but not all vertices. Okay? What does that mean in this context? So we remember we have an endpoint set capital P, and we are going to define what is called a unit distance graph. The vertices of that graph are precisely the points in capital P, and we are going to join two vertices by an edge only if their distance is 1. So if it obeys the correct property. Okay. So then what is U of n? Remember, U of n was the largest value of such pairs of points. Therefore, in the graph theoretic language, U of n is the maximum number of edges that such a graph can have. Okay. So one can reframe the unit distance problem by saying, what is so special about a unit distance graph that can give us some insight into controlling U of capital N? That's the question. Okay. So now comes a geometric observation of Erdős. So let's try to walk through it slowly together. Okay. So you see there are 5 points here, A, B, A prime, and PQ. So these are all points in my vertices of my unit distance graph. Okay? And you see some of them are joined by edges. And do you remember what joining by edges means? Joining by edges means that the distance between Q and A is 1, the distance between Q and B is 1, distance between P and B is 1, and so on. Okay. Now, let's take a look at if we take up the point Q and we draw a unit circle around it, this is one of these red circles, it passes through A and it passes through B. Similarly, if I draw a circle centered at P of radius 1, this is a blue circle, it passes through A and it passes through B. Good. Now I'm going to look at another point, A prime. And A prime is actually a unit distance away from Q, which means that when you look at the red circle, it actually passes through A prime as well. Question to you, can this A prime lie on the blue circle? Is it possible, now that I know that A prime lies on a red circle centered at Q, is it possible that this A prime will also lie on a unit circle centered at P, namely this blue circle? It's not possible, and why is that? A and B are already have intersected. We are talking about circles on the plane. We have exhausted the total number of intersection points. Okay. So, the fact that A prime cannot lie on the blue circle, it has a very particular technical meaning in the graph theoretic language. So I'm going to draw a picture for you here. So let's say we have on one side P and Q. So this is P, this is Q. And is everybody able to see here? Okay. And on the other side there is A prime, B. So A prime, B. Okay. So PA, PB are joined. QA and QB are joined, but and QA prime is also joined. What I want to say is that this is not possible. If this were possible, for the moment, if this line could actually be an edge, this would be called a bipartite graph. This would be called a K23 bipartite graph. Why bipartite? Because there are 2 on one side, 3 on the other side, and everybody joins with everybody else. But that's not possible. This is not unacceptable configuration. This is what is called a forbidden configuration. So, a unit distance graph has the property that it has to be free of the structure K23. So, K23 is a forbidden structure, and the reframed unit distance problem now says, what can we say about the number of edges of a K23 free graph? So what is the maximum number of edges in a K23 free graph with n vertices? Okay. So this way of looking at a problem has really brought about a genuine paradigm shift in the study of distance problems, in the study of combinatorial geometry. Nowadays, it is standard practice when trying to solve a geometric optimization problem, you first extract a combinatorial property of the underlying structure, which is like to find a graph, like the unit distance graph. Then we ask, can we associate a graph or a hypergraph H with the geometric situation? So what is the graph or the hypergraph in our case? The edge consists of pairs of points, unit distance apart. That's the capturing the geometric situation. And if there is such a graph, then we ask, can we exclude a forbidden configuration H0? And if so, we establish a number of edges in an H0 free graph. And this methodology in many manifestations has permitted all of combinatorial geometry, including Erdős's own problem and Spencer, Zemeredy, and Trotter, and many other results. Okay. All right, so let's take a break and see if you have any questions.
Okay, you are repeatedly talking about distance 1, and we are considering this R2 plane where all real numbers are possible, so distance can be a little bit infinitesimally larger than 1 or infinitesimally smaller than 1. So how do you define 1 in such a situation?
Because you see, we are in RD. If the 1 is actually irrelevant, you could pick your favorite number. Let's say your favorite number is pi. Okay, so let's go back to the Erdős unit distance problem.
So how close two distances have to be to conclude that they are the same distance?
I see. Okay, so you are talking about what are sometimes called almost distances, or sometimes called fuzzy distances. Okay, so in the continuum setting, so right now, since we are talking about exact points, all distances are exact. There is like no room for error. Okay. But one of the things that I have noticed is that applied mathematicians and computer scientists hate exact. They want everything up to an error. Okay. So there is the slightly fuzzed up version where instead of taking a point, you look at delta balls around the point. So your set is really a union of delta balls. So distances are not exact anymore. All distances, first of all, these points to be considered different have to be more than 2 delta apart so that they can actually pick up something. And distances are allowed a fudge factor of delta on either side. And such results are also abound in the literature. So, yes.
So, you only extracted the property that K23 cannot be there.
Correct.
Like, similarly, if one might work a little bit more and then extract some other forbidden subgraph.
Yes.
So, can you use all of them together to maybe...
That is exactly how these improvements were obtained. So all I am showing you here are basically the tips of the iceberg. So K23 is a forbidden configuration, but it is by no means the only forbidden configuration. Now you can take a forbidden configuration that actually contains K23, which makes the forbidden configuration even more complex, which makes the bound on UN better. Yes. Okay.
There
I don't know. Maybe the right person to answer this question would be a combinatorial geometer. But the bottom line is that even though it is framed in a graph theoretic language, driving the graph theory is the actual geometry of how circles intersect. So the more information that you can extract about the intersections of families of circles of radius 1, the better ultimately your bound will be. Okay.
So the one that you have taken in it is,
Yes.
I mean, if I'm going to take something else, does it make the problem more complicated?
No. As I think when I misunderstood your question, I thought you did not like 1 somehow and you wanted to put a different number there. I think Sundari is asking that question, right? So it makes no difference. You could take a point pi here, and all you would have to do is replace this point capital P by P over pi, and it just, by a scaling, it becomes the exact same problem. Okay.
There are a set of distances. So unit distance, you could have distance 1, 2.
If you want like vector valued distances, yes. So like if you want, meaning that here you want 3 point, let's say you want a P, Q and an R, where P and Q is separated by 1 and let's say P and R is separated by 2. That's one, but you meant something else.
The distance could be is 1 or 2.
Is 1 or 2, yes, yes. I don't know of a result of that ilk, but I'm not sure. It doesn't mean it doesn't exist, but off the top of my head, I don't know. Yeah. Yes, but there are things called multi-distances that I know, which are where you have actually, instead of looking at just distance between a single pair, you look at a vector, and each vector is a distance. Yeah. So everything that I have talked about so far is about in the discrete setting. I now want to move over to the continuum. Okay. So the distance problem in the continuum setting have a slightly different flavor for obvious reasons. Sets are typically uncountable. Of course, so looking at cardinality of the set is a no-go. We need measures to capture the notion of largeness, not the counting measure. And of course, as we all know, the first stop in measure theory is Lebesgue measure, which I'm going to denote by lambda sub d in RT. Now, a very long time ago, Steinhaus in 1920, and I don't know if this result I think pops up in almost every measure theory book in some form, and generalized by Picard in 1942, says the following. For in any dimension D, a Borel set E of Rd of positive Lebesgue measure has the following property, that the different set E minus E contains a ball centered at the origin, and because the distance set is just the absolute value map applied to E minus E, the distance set contains an interval of the form 0 to A for some positive A. Okay. Remember at the very beginning of the talk, I said there is this one meta principle that you need to hang on to. Large sets have large distance sets. So here is another rendition of that fact. Here is a set that is large being measured in Lebesgue measure. It will have a large distance set. Large distance set means that it will contain an interval. Okay. All right. So this is Steinhaus, looks very serious. Okay. I'm not going to prove to you Steinhaus's original theorem. You may, oh my gosh. Hi Purvi, sorry, I did it. So in the original Steinhaus's theorem, you may already have seen many proofs of it. The result that I want to talk to you about is something called a universal Steinhaus theorem, and I'll tell you what that means. So it was actually discovered by Bodeman in 1970, and it says the following, that suppose, it goes back to this question of how does the length of this interval 0 to A, how does this A depend on the Lebesgue measure of E? That's what it goes back to. And the question is it possible that this A doesn't only depends on the size of E and not on E itself? Okay. And Boardman proved that the answer is yes if the Lebesgue measure of E is larger than half, and the answer is no if the Lebesgue measure of E is smaller than half. Okay. Remember also that this is only a result in dimension 1. It has generalizations in dimensions higher, but it's not as sharp in higher dimensions. So what does this result say? It says that there is, for every lambda larger than half, you can find an absolute constant C lambda such that no matter what Borel subset of E of the unit interval E you choose with Lebesgue measure at least lambda, the distance set of E is bound to contain the fixed interval 0 to C lambda. And this is a proof that I promise you we can actually work out together right now in this talk. So I'm just going to go over this with you. So if lambda is larger than a half, 2 lambda is larger than 1. And if 2 lambda is larger than 1, we can find a small constant C such that 1 plus C is dominated by 2 lambda. Okay. What I want to show is that this C is that C lambda. In other words, that delta E contains 0 to C. That's what I want to show. Okay, so pick a E in 0 to 1 of Lebesgue measure lambda, and you pick any point x in this interval, and I want to show that x is in the distance set. Okay, so we are going to look at E union E shifted by x. Okay, E is a subset of 0, 1. X plus E is a subset of x comma 1 plus x, and x is less than or equal to C, so this entire union is contained in the interval 0 to 1 plus C. Okay. So if I look at the Lebesgue measure of this union, it is of course less than or equal to the Lebesgue measure of this entire interval, which is 1 plus C, and by our choice this is strictly smaller than 2 lambda, and because of the translation invariance of the Lebesgue measure, 2 lambda can be written as the sum of the measure of x plus E and the measure of E. Now, we know that if the measure of a union of two sets, A union B, is strictly smaller than the sum of the measures, lambda of A plus lambda of B, that means that these two sets must have an intersection, otherwise it would be an equality. So what does that mean? That means the intersection is non-empty, and that means that x actually belongs to E minus E. And remember, we are in dimension 1, so E minus E is the same as delta E, which means that x belongs to delta E, and because this was true for an arbitrary x in 0 to C, delta E contains 0 to C. So we are not often so lucky in this business to have these 5-line proofs. When they happen, they're very rare and very coveted, so I thought I'd share. Okay. All right. So from this point onwards, don't pay too much attention because I'm going to go over all of this again tomorrow anyway when I delve into the more analytical side of things. Once we get past the situation for Lebesgue measure, there are tons and tons of sets which are extremely rich in structure but which are Lebesgue null. So the Lebesgue measure is unable to capture the size of such sets. It's just too thick of a calibration to kind of compute the content of that set. And yet those sets occur all over the place, and we would like to understand the structure of their distance set. So how do we measure size of sets that are Lebesgue null? There are many ways, but at least for this talk, there are these two notions that I would like to tell you about or remind you for those of you who are already in this business. So the notions are of Hausdorff measure and Hausdorff dimension. So suppose that capital A is a Borel subset of Rn, and S is an exponent between 0 and n, not necessarily an integer. So one defines the S-dimensional Hausdorff measure in the following way. You pick a delta and then look at a covering of A by balls of radius at most delta. So you have, let's say, sort of uncountably many points. This is your set. You try to cover this by in as efficient a way as possible, with the constraint that it's a countable covering and the radius of the balls that you are using are no more than delta. Okay. And for each covering, you compute this summation Ri to the S, look at the infimum over all possible covers and take the limit as delta goes to 0. That's your S-dimensional Hausdorff measure. Okay. Associated to Hausdorff measure is the notion of Hausdorff dimension. It's known that there is kind of a cliff, so above which the S-dimensional Hausdorff measure, there is a cliff below which the S-dimensional Hausdorff measure is infinite, and then you kind of drop off the cliff and all the S-dimensional Hausdorff measures become 0, and this threshold value of S where this happens is the Hausdorff dimension of A. Okay? So when Lebesgue measure fails, this is the way, this gives an alternative way to measure size. And just to sort of as a sanity check, you are all probably familiar with the notion of topological dimension. So lines have topological dimension 1, surfaces have topological dimension 2, and those notions actually agree with the notion of Hausdorff dimension. So at least we are not doing something totally crazy here. But in situations where topological dimension doesn't make sense, Hausdorff dimension often continues to make sense and gives a fractional notion of dimension, which is extremely important in geometric measure theory. So for example, here is like a quintessential example of a fractal called the Sierpinski triangle. It, of course, topology is a very rough object. It's not a manifold or anything, so we can't compute a topological dimension, but it has Hausdorff dimension log 3 over log 2. Another important example, very classical, very important in physics, in finance, what have you, everything, in probability, is the graphs of Brownian motion. So these are, once again, they have a fractional dimension. This is in R2. They have almost surely the graph of a Brownian motion path has Hausdorff dimension 3/2. Okay. So I am going to conclude to wrap up today by going from Steinhaus's old 1920 result to the next most natural thing that one could possibly ask, which stands as one of the notorious open problems in the field called the Falconer distance set conjecture. So again, remember, large sets should have large distance sets, except Falconer conjecture, formulated largeness in terms of Hausdorff dimension. So he asked if E is a subset of Rd and the Hausdorff dimension of E is at least as large as half of the ambient dimension, D, then delta E has positive Lebesgue measure. Large sets has large distance sets. Okay. Now, this is probably one of the most hotly contested results in or conjectures in geometric measure theory. Lots of work has been done on this. I am sort of listed a few. There are many, many more. In dimension 2, the best known bound stands at 5/4. It ought to go down to 1. And in dimensions D larger than or equal to 3, this is the currently known bound. So remember, everything that's not D/2, this extra bit, this is what one needs to get rid of. And along the way, while proving these results, there have been many exciting new connections that have emerged of this problem with Fourier restriction problem, decoupling, projections, incidence geometry, all of which are pillars in harmonic analysis and measure theory. Okay. So in tomorrow's talk, what I wanted to talk to you about is really not one result, but rather a network of results in distance sets. Okay, so I want to talk, I didn't have enough time today, but I'll tell you what it means for a set to contain all distances and or all sufficiently large distances, and then after that I will tell you what is known about them and what, well, this particular talk tomorrow has a very interesting IISC connection, so I should tell you about it. At some point, I don't know, Nadu, if you remember, whether it was 2012 or 2015, at some point, he mistakenly somehow invited me to give a talk, a lecture series in something, fractals? I forget, in something. And Rani was one of the students in that course. So we ended up chatting, and that chat ended up in more conversations, and we ended up working on a problem on distance sets. And some of these results that I want to talk to you tomorrow about are actually, I'm not going to torture you with complicated proofs, but I want to motivate what kind of questions led to the problems that we discussed and what remains to be done. So what I want to do today is I will stop here because I want to leave some time for Q&A, but if you want, I can give you more details as we go. Okay, so that's where I want to stop today, and thank you. Yes, yes. So there, let's go back. I want to maybe say a couple of things here. So first of all, this d greater than or equal to 2 is important. The conjecture is false in dimension d equal to 1. Plus, this constant d over 2 is sharp. There are examples that show that if the dimension is less than d over 2, then this delta of E has Lebesgue measure 0. In fact, there is a stronger version of this conjecture which says that, well, maybe a refinement, not a stronger version, that if the dimension is larger than or equal to d over 2, then the Hausdorff dimension of delta E is d. That's the other. For strictly larger than d over 2, this is the stronger conjecture. For dimension equal to d over 2, the fact that the dimension of this is equal to d, that's the new addition. Yes.
Is there anything known for different notions of distance within RD, like to take a different norm? Is there any results? Are there results known for that?
Yes. There is a lot known, so they're all hiding here, okay? So if you look at, for example, Konyagin and Laba, they look at not the Euclidean distances, but actual like L infinity distances. Results are very different. And this more recent paper by these 3 authors, once again, they look at a different distances generated by norms that emerge from certain convex bodies. Not the convex body is no longer the circle, but it's a different norm. And they show that the Falconer distance set conjecture in that setting is actually false.
Any more questions?
So I'm checking the chat.
Yes.
There is no question there.
Okay.
But somebody said that the question I asked
Yes.
has an easy resolution, and they gave some reference to a paper by 3 authors in 1977
Okay.
on 2 distance sets in Euclidean.
Okay. Great. Okay.
Norman, Rogers, and Sider.
Okay. Maybe you should send that to me as well, because I was not aware.
I will.
Yes.
Thank you to the
Yes.
answer.
Yes.
They can hear us.
Yes.
There are no more questions. Let's thank the speaker for the talk.